Welcome to this problem walkthrough. Today, we will explore LeetCode problem number 796, rotate string. This problem challenges us to determine if one string can be transformed into another through rotations. We'll break it down step by step, analyzing different approaches along the way. Let's get started. In this problem, we are given two strings, s and goal. The goal is to determine whether string s can be transformed into goal by performing a series of shifts. A shift involves taking the leftmost character of s and moving it to the rightmost position. For example, if s is ABCDE, applying one shift would result in BCDEA. The task is to return true if it is possible to turn s into goal using any number of such shifts, otherwise, return false. The input consists of two strings, both of length n, where n is between 1 and 100. The output is a Boolean value, true if the transformation is possible, and false if it is not. Let's look at some examples to better understand the problem. In the first example, s is ABCDE and goal is DEB. After performing two shifts on s, we get goal. The first shift changes s to BCDEA, and the second shift changes it to DEB, which matches goal. Therefore, the output is true. In the second example, s is ABCDE and goal is abst. Here, no matter how many shifts we perform on s, it is not possible to turn it into goal. As a result, the output is false. In the third example, both s and goal are the single character a. Since the strings are already identical, no shifts are needed. This means the output is true. These examples illustrate the various scenarios you might encounter, including cases where the strings are identical, or where it is impossible to produce goal from s through any number of shifts. Now, let's consider the constraints and some edge cases. The lengths of s and goal range from 1 to 100, and both strings consist only of lowercase English letters. For edge cases, if s and goal are identical strings, the output should always be true, as no shifts are required. If the lengths of s and goal are different, the output must be false, since rotations are only possible when the strings have the same length. For single character strings, the output is true if they are the same character, and false otherwise. Lastly, if no sequence of shifts can make s equal to goal, the output should be false. These constraints and edge cases help in understanding the boundaries of the problem and ensure your solution handles all possible scenarios. To solve the rotate string problem, we considered two main approaches. First, the brute force approach, which relies on simulating all possible rotations of the string s and checking if any of them matches the string goal. The intuition here is straightforward. By repeatedly moving the first character of s to its end, we can generate every possible rotation. The process involves iterating through all len, s, rotations, creating the rotated version of s each time, and then comparing it with goal. If any rotation matches goal, we return true, otherwise, we return false. However, this approach has a significant drawback in terms of efficiency. Generating each rotation takes n time, and there are n total rotations, resulting in a time complexity of n squared. Additionally, the space complexity is n, because we need to store intermediate rotations. Given these inefficiencies, we explored an optimized approach. This alternative method is based on the observation that if s can be rotated to match goal, then goal must appear as a substring of s plus s, the concatenation of s with itself. By doubling s, we effectively simulate all possible rotations as substrings, allowing us to check for goal in a much simpler and faster way. This optimized approach, often referred to as the double string method, involves a few straightforward steps. First, we ensure that the lengths of s and goal are equal, as a mismatch in length would immediately rule out the possibility of one being a rotated version of the other. Next, we concatenate s with itself to create the string s plus s. Since this new string contains all possible rotations of s as substrings, we can simply check if goal is a substring of s plus s. If it is, we return true, otherwise, we return false. The strength of this approach lies in its efficiency. Checking substring membership is typically a linear time operation, giving this method a time complexity of n, where n is the length of s. The space complexity is also n, to store the concatenated string. Additionally, we briefly considered using string searching algorithms like KMP, or Knuth-Morris-Pratt, as an alternative to the built-in substring check. The KMP algorithm pre-processes the pattern to improve search efficiency, maintaining the same O(n) time complexity. However, it introduces additional complexity in implementation, as it requires constructing and using auxiliary data structures like the prefix table. While theoretically equivalent in efficiency to the double string method, KMP is more intricate and less practical for this problem. Among the approaches considered, we ultimately selected the optimized double string method due to its simplicity, efficiency, and ease of implementation. The brute force approach, while intuitive and easy to code, was ruled out because its O(n)² time complexity makes it impractical for larger inputs. On the other hand, the double string approach leverages Python's highly optimized internal substring checks, making it both fast and straightforward. Although the KMP algorithm also offers O(n) time complexity, its added complexity in implementation and debugging does not provide any practical advantage for this specific problem. When comparing the trade-offs, the double string approach stands out as the most balanced solution. It is significantly faster than brute force, avoids the overhead of custom algorithm implementation like KMP, and requires only O(n) space, which is consistent across all considered approaches. By choosing the double string method, we achieve an elegant solution that maximizes efficiency while minimizing implementation overhead, making it the ideal strategy for this problem. In this problem, we're tasked with determining whether one string is a rotation of another. A rotation involves shifting characters from the front of a string to the back while maintaining their relative order. The brute force approach to solve this problem is straightforward. First, we check if the lengths of the two strings are equal, as unequal lengths immediately rule out the possibility of one being a rotation of the other. Next, we simulate all possible rotations of the string S by repeatedly moving the first character to the end and comparing the resulting string to goal. If at any point the rotated string matches goal, we can conclude that goal is indeed a rotation of S. Otherwise, after exhausting all possible rotations, we return false to indicate that no match was found. To exhaust all rotations, we start with the original string S and iterate through all possible rotations by repeatedly shifting the first character to the end. For each rotation, we check if the modified string matches the goal. If a match is found at any step, we return true. Otherwise, after completing all rotations, we return false. The provided code implementation demonstrates this process. It begins by validating the input lengths to ensure they're equal. Then, it simulates each rotation using string slicing and concatenation, comparing the result with goal. This brute force approach ensures that all rotations are considered, but it can be computationally expensive for longer strings. To improve efficiency, we can use an optimized approach based on string concatenation. The key insight here is that concatenating S with itself produces a string that contains all possible rotations of S as its substrings. For instance, if S is ABCDE, then S plus S becomes ABCD, which includes all rotations of S within it. Using this property, we can check if goal appears as a substring in the concatenated string. First, we validate that the lengths of S and goal are equal. Then, we create a new string by concatenating S with itself and use Python's efficient substring operation to check for the presence of goal. If goal is found in the concatenated string, we return true, otherwise, we return false. This approach avoids the need to explicitly generate and compare rotations, making it significantly faster. Comparing the two approaches highlights some key differences. The brute force method generates each rotation explicitly, leading to a time complexity of O(n)², where n is the length of the string. On the other hand, the optimized approach leverages string concatenation to eliminate the need for explicit rotation generation, reducing the time complexity to O(n). The reason the concatenation trick works is that duplicating the string naturally incorporates all potential rotations as substrings. This insight drastically simplifies the problem. It's also important to consider edge cases. For instance, if both strings are empty, we return true, as an empty string is trivially a rotation of itself. If the strings are identical, we can return true immediately without further checks. Finally, if the lengths differ, we can return false right away, as rotations are only possible for strings of the same length. The optimized approach introduces the use of a doubled string, which is the concatenation of S with itself. This single string allows us to check for rotations efficiently without generating them explicitly. In terms of complexity, the brute force approach has a time complexity of O(n) squared, due to the repeated generation and comparison of rotations, while its space complexity is O(1). The optimized approach reduces the time complexity to O(n) by using the n operator for substring checks, but it has a space complexity of O(n) for storing the concatenated string. Overall, the optimized method is more elegant and practical, especially for larger inputs. By leveraging the fundamental property of string rotations, it avoids unnecessary computations and provides a cleaner solution to the problem. The problem requires us to determine if one string is a rotation of another. A rotation involves cyclically shifting the characters of a string. For example, rotating ABCDE to the right gives EBT. To solve this efficiently, we first check if the lengths of the two strings, S and goal, are equal. If they differ, it is impossible for one to be a rotation of the other, so we return false immediately. Next, we create a new string S_double by concatenating S with itself. This simulates all possible rotations of S because any rotation of S will appear as a substring within S_double. For example, if S equals ABCDE, then S_double equals ABCD. ABCDE contains all rotations of S within it. Finally, we check if goal is a substring of S_double using the in keyword. If it is, then goal is a valid rotation of S, and we return true. Otherwise, we return false. This approach is efficient due to the substring check, which operates in O(n) time complexity, where n is the length of the strings. The overall space complexity is also O(n) due to the creation of the doubled string. This is the Java implementation of the rotate string problem, which mirrors the Python logic. The solution first checks if the lengths of the two strings match; if not, it returns false. Otherwise, it concatenates the string S with itself to simulate all possible rotations. Then, it checks if the goal string is a substring of the concatenated result. The key differences are the use of Java's string dot contains method and explicit type declarations for variables and method parameters. Let's continue. Let's continue. Let's continue. The time complexity of this solution is O(n), where n represents the length of the string S, which is the same as the length of goal since the function only returns true if their lengths match. Let's break this down step by step. First, checking the lengths of the two strings using len, S equals len, goal, takes O(1), because Python pre-computes string lengths, so retrieving and comparing them is constant time. Next, the operation S_double equals S plus S involves concatenating two strings of length n. This requires O(n) time, as Python creates a new string and copies all the characters from both instances of S into the new string. Finally, the substring search operation, goal in S_double, has a worst-case complexity of O(n). Python implements this using optimized substring search algorithms, such as Knuth-Morris-Pratt or Boyer-Moore, which ensure linear time performance for this scenario. Combining these steps, we see that the overall time complexity is determined by the substring check, making it O(n). Since the substring search dominates the time complexity, the overall time complexity of the solution is O(n). Let's now analyze the space complexity. The space complexity is also O(n). Here's why. First, the input strings, S and goal, are not modified during the function's execution, meaning they do not require additional space. However, the concatenated string, S_double, does require extra space because it stores a new string that is twice the length of S. This means S_double contributes O(n) space. Additionally, the function does not use any auxiliary data structures, so no further space is consumed. As a result, the overall space complexity is dominated by the memory required for S_double, making it O(n). To understand why this approach is efficient, let's compare it to a brute force method. A naive approach would involve generating all possible rotations of the string S and checking if any of them matches goal. Generating these rotations would take O(n) squared time because there are n rotations, and constructing each rotation involves O(n) operations. On top of that, the space complexity of storing all these rotations would also be O(n) squared. In contrast, our optimized approach reduces the problem to a substring search by concatenating S with itself, which takes O(n) time and O(n) space. This is a significant improvement over the brute force method, especially for larger strings. To summarize, the optimized approach achieves a time complexity of O(n), dominated by the substring search, and a space complexity of O(n), due to the concatenated string s_double. This makes it far more efficient than the brute force approach in both time and memory usage. When solving the rotate string problem, there are a few common mistakes to watch out for. First, failing to handle edge cases properly can lead to incorrect results or runtime errors. For example, if the strings s and goal are of different lengths or one of them is empty, the rotation is invalid, so this check needs to be done up front. Another common issue is incorrect rotation logic, such as shifting the wrong characters or modifying the original string in ways that break the rotation process. This can lead to invalid comparisons. Additionally, some solutions use nested loops to simulate all possible rotations and compare each to goal. While this approach may seem straightforward, it has a time complexity of O(n²), which is inefficient for large inputs. Finally, overlooking the optimization of using string concatenation can make the solution more complex than necessary. Checking if goal is a substring of s plus s simplifies the problem significantly and avoids unnecessary computations. Another mistake to be mindful of is ignoring space complexity. For instance, creating new arrays or strings unnecessarily, especially in brute force approaches, can quickly lead to excessive memory usage, which is inefficient for constrained environments. Now, let's focus on some critical interview insights. The key takeaway is that a rotated string can be checked efficiently by determining if goal is a substring of s plus s, which reduces the problem to a substring search. This approach is both elegant and efficient. Recognizing this pattern demonstrates a solid understanding of string manipulation and optimization principles, which is why this problem is a popular choice in interviews. Be prepared to discuss the trade-offs between brute force methods, which are easier to implement, and optimized approaches that are more efficient but require deeper insight. Also, remember to highlight edge cases, such as strings of different lengths, empty strings, and cases where s and goal are identical. Interviewers might also explore follow-up questions, such as how to handle additional constraints like limiting space complexity. This problem shares similarities with other challenges that involve string manipulation and substring logic. For instance, LeetCode 28, which is about finding the index of the first occurrence of a substring, and LeetCode 186, which deals with reversing words in a string, both require careful handling of string operations. Similarly, LeetCode 151, which focuses on reversing words, has operations that are conceptually similar to rotations. Understanding these related problems can help reinforce your grasp of string manipulation techniques. Now, let's consider alternative approaches to solving rotate string. One approach is brute force simulation, where you generate all possible rotations of s and compare each to goal. While this method is easy to understand and implement, it has a time complexity of O(n²) and uses O(n) space, making it impractical for larger inputs. On the other hand, the optimized solution using string concatenation checks if goal is a substring of s plus s, reducing time complexity to O(n), and keeping space complexity at O(n). This approach is both efficient and elegant, but it requires a good understanding of substring mechanics. For those looking to push efficiency even further, advanced substring matching algorithms like KMP or Knuth-Morris-Pratt can be applied. The KMP algorithm pre-processes the input to build a partial match table, allowing for efficient substring searches. This approach maintains a time complexity of O(n) and a space complexity of O(n) for pre-processing. While it is extremely efficient, it does require familiarity with how the algorithm works, making it a more advanced option. Mastering these techniques not only strengthens your problem-solving toolkit but also showcases your ability to handle more complex algorithms, a skill that is often valued in interviews. Great job! To recap, we explored the rotate string problem and discussed the brute force approach. We highlighted its inefficiencies and key concepts like string rotations and edge case analysis. Thanks for watching, and be sure to like and subscribe for more problem-solving insights. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!